Yo, what is up, guys? Welcome back. I think episode 86 today. Or is it 85? Maybe it's 85. Our dog trio today. So it is 85. Take a listen to the sound, shall we? There is our sound. Oh. Gotta fix this mic. There we go. Okay. I think that's good. Alright. Yeah. Let's take a look. So, just a little update. I did start looking at... I was watching a graph here. I was actually watching this one. I'm a little bit further now. I'm probably about... Yeah, I just did the shortest path, so... I think I'm at about here in the video.
Awesome.
I've actually learned a lot.
So be sure to
really
practice
good.
this algorithm
So,
before you move on. And do make sure while you
I'm feeling a little
understand
more
the choice
confident.
of breath first here over calculate a short way. Over to the approach for this island count.
I'm feeling a little bit more confident. But obviously I feel like I gotta show that in the code. Let's take a look. It's that same one we did yesterday. On maximum value over all triplets of indices. Let me think here. Really, bro? My mic goes back up to being super. Okay, remember I has to be the greatest value, right? So is equal to the max of, because we're finding the largest value, right? Max underscore k. Max of max underscore k. trying to think here. Max I, Max J, Max K. I know we want to return a Max K. Well, no, we're passing in the indices here, so this has to just be max underscore I. Underscore I or nums J. Right. And max K would be the max K, the max I, minus the nums J, because it's the J loop. Our K has to be Bro, what is wrong with my mic right now, bro? I'm not sure. I have to look back. Let's start this at first value, right? Max J. Things will just be max J. We need something else. How we calculate K? Why is K always an X value? Max J. There we go. Maybe I should leave a comment, bro. Should I leave a comment? How do I comment? We'll keep firing gas problem. Something stupid like. Okay, my shelf reputation, bro. All right. Oh. Last little Japanese candy. Ooh. Alright, take a look at that. Should clone graph. What is going on, bro? The graph is represented in the chat case using an adjacency list. I'm confused what I have to do here. Return a deep copy clone of the graph. I'm confused a little bit. Curious, I want to print the node. So I think from what I can understand in this problem is that we're given a node and that node leads to each point of the graph. Let's do like cur is equal to node. Wow. What code is not equal none? Let's create like a visited so we can get out of this loop. Make a set here and cur not in visited. Sorry for that burp. Do cur.val. Sorry. Visited.add cur. Cur is equal to. Sorry, then we print cur, print cur.val, and then we increase cur is equal to cur.next. There's no attribute next. I'm so confused right now, bro. I'm so confused. Are we given an adjacency list or are we given a node? You iterate over cur.neighbors. The fuck? Cur.neighbors. Okay. Well, let's do like a simple like BFS traversal. I don't know. That's pop. Q. Oh, sorry. No. Sorry. Let's do like cur is equal to q dot pop left. Okay, let's print. Visit all the neighbors. So we go for. How do they do it? For I in cur.neighbors. Visited. There's no attribute val. Like, bro, what? Has no attribute val. Like. Okay, bro, I'm so confused right now. Like, generally, like. So confused. Dictionary to store original node. Bro, I'm so confused with this problem. Like, I'm honestly not even sure, like, how to even go about this problem, bro. Like, okay, Leetcode has one.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem clone graph. So we're given a reference to a node that is in a connected undirected graph, so it's convenient for us that the graph is completely connected. And all we want to do is return a deep copy of that graph, in other words, a clone of that graph. And for every single node, we have two things. We are given a value, and we're also given a list of its neighbors. So this is what's telling us, how the graph happens to be connected. These are the edges in our graph. Now, if you're not super familiar with what a deep copy is, so let's say that this is our example, our input graph. We're not just going to create a shallow copy, meaning like this is the exact same graph, like the color is yellow for both of these, meaning like it's the exact same graph. We didn't actually create a clone of it. So this is not what we're looking for. This is also not what we're looking for. So this is a new graph because the color is slightly different. But you see that the values aren't exactly how they're supposed to be. We have a 3 here, whereas we have a 2 in the original graph, right? So basically we have these twos values mixed up. So that's not what we want either. We want an exact clone. So it has the exact same structure and values, right? The values and structure is the exact same. And this happens to be a new graph. This is not the exact same graph as this one because this one is blue, whereas this one is yellow. So how are we going to solve this problem? Well, you can see I'm going to use a hash map like pretty much every graph problem, and we're going to use depth first search, where you can also use breadth first search if you want, but let me show you the general algorithm. So you can see these edges are undirected, meaning,
I'm more just confused about the nodes. How to work with the nodes. I'm so confused about this problem.
Neighbor 1 in its neighbor list. So let's say that 1 is our entry point in the graph. What are we going to do? You can see initially our hash map is empty. What we're going to try to do is map the old nodes to the new nodes or the copy nodes. So we start at 1. So what's the first thing we should do? Well, obviously we should create a copy of this node. That's what I'm going to do. So create a copy of 1. Now this copy of 1 is not complete yet, right? Because take a look at the original one. It has 2 neighbors, 3 and 2. So what can I do? We know we're going to have 2 neighbors for node 1, right? Can I just take these 2 original nodes and then put them over here, 3 and 2? No, I can't do that because for these nodes 3 and 2, we actually have to create copies of them as well. So you can see that this is going to be recursive. So first thing I'm going to do is I'm going to go to its first neighbor, which let's just say it happens to be 2 in this case, right? So I'm going to start cloning starting at 2. So we're at 2, we're going to create a clone of 2. Oh, and by the way, before I forget, before we make a clone of 2, we know we just created a clone for 1. So what are we going to do? We're going to map the original node 1 to its now clone node 1. So we're mapping the old node to the new node. And I'm going to show you why we're doing that in a second. So now we're going to go to node 2, right? And we're going to create a clone of node 2. So let's create that clone node 2. We're also going to add it to our hash map, right? We're mapping the old node 2 to its clone. So the clone in blue is the new node. So now we've cloned 1 and we've cloned 2. And for 2, now let's look at 2's neighbors. Well, look, you can see that it has a neighbor of 1, right? And it has a neighbor of 4. So first we're going to end up trying to do is create a clone for 2 because we know that we have to, in the list of neighbors for 2, we have to add the clone 1, which we haven't done yet. So what we're going to end up doing is we're going to try to clone 1, but we're going to see in our hash map, look, we already ended up cloning 1. So basically what I'm saying is now we can say, okay, we can add this edge that 2 is connected to 1, that 2 has a neighbor that happens to be 1. And basically, the reason I'm doing that is because we know this edge is going to be undirected. It goes both ways. So that's what I'm trying to do here. So now we know that 2 is connected to 1. We also know we have to clone node 4. So now we're going to visit position 4. Let's create a clone for 4. So let's add it to our hash map as well. We're mapping the original node 4 to its clone. So now we're at the node 4. We want to clone 4's neighbors. First, you see that 4 has a neighbor 2, which we already cloned. So we're going to clone of the most is 4. So we're going to say, okay, we know that this 4 needs to have a clone, but the good thing is we already created a clone for that node, and this is 2, 4. So we're going to make this edge basically double directed. And 3 also has another neighbor of 1. And so basically what we need to do is make a clone of that 1, but we look in our hash map first and we see we already cloned 1. This is the clone. So we're going to take 3 and connect it to 1, right? But wait, we have one last problem, right? This 1 should also be connected to the 3, right? You're right. And that's what we're doing recursively now. So we originally started at 1, then we went to 2, then we went to 4, then we went to 3. Now what we're going to end up doing is reversing that because we remember we're doing this recursively. So we're going to pop back up to 4. We're going to see 4 has already cloned its neighbors. 3 already cloned its neighbors. We're going to pop back to 2. 2 already cloned its neighbors. We're going to pop back to 1. 1, we ended up cloning the neighbor 2, right? But we didn't end up going this way. So from 3 now, we're going to end up checking, okay, did we already clone 3? Let's look in our hash map. Yep, we already did. So this is the clone that we created. So all we really need to do is make 1 connected to 3, so basically make this edge double directed. So now you can see that we finally created a complete clone of the graph. We did this in O of n time, where n is basically the number of edges plus the number of vertices, right? The number of nodes plus the number of edges connecting them, because we have to basically make a clone of each of these. And with that being said, now let's jump into the code. Is a hash map. We remember that we only need a single data structure, old to new, which is a hash map mapping the old nodes to the new nodes. And I'm going to implement this in depth first search. And you can see that this function is nested in the outer function, which just makes things easier, meaning that this data structure doesn't need to be passed into every single function call, but we do need to pass in every time the node that we're visiting. So in depth first search, we're going to pass in the node. First thing we're going to check is if the node is in our hash map. If it is in our hash map, then that means we already made a clone of it. If we already made a clone of it, then I'm just going to return that clone. We don't need to create another clone. So if it exists, return the new node. So if this statement doesn't execute, that means a clone doesn't already exist. So let's create that clone. I guess I'll call it a copy. So we're going to create a copy of this node. So we're going to use the node constructor, and the value we're going to give it is the value of this original node. And we're also going to take that copy and then add it to our old to new hash map. So old to new. So the old node is just node, and the new node is the copy. So we're mapping the old node to the copy. And then we want to make copies of every single neighbor of the original node. So node.neighbors. Let's go through every single neighbor and let's run depth first search on that neighbor. And so basically, if we run depth first search on that neighbor, what it's going to do is it's going to return the copy that we end up creating. And with that copy, what am I going to do? I'm going to take this old node or this new node, the copy that we made, and I'm going to take its list of neighbors, and I'm going to append to that list of neighbors this the return statement from this depth first search call. So let's copy and paste that in here. So that's all I really need to do, depth first search, and add it to the neighbors of this copy that we just made. And once we're done making all the copies of this, all end, what I'm going to do is it's going to return the copy that we end up creating. And with that copy, what am I going to do? So we're mapping every single. Let's go through every single neighbor and let's run depth first search on that neighbor. And so basically, if we run depth first search on that neighbor, what it's going to do is it's going to return the copy that we end up creating. And with that copy, what am I going to do? I'm going to take this old node or this new node, the copy that we made, and I'm going to take its list of neighbors, and I'm going to append to that list of neighbors this the return statement from this depth first search call. So let's copy and paste that in here. So that's all I really need to do, depth first search, and add it to the neighbors of this copy that we just made. And once we're done making all the copies of the neighbors, then we can return the copy that we just made in the current function call. And it's actually that simple, because even though this is called depth first search, it might even be better to call this function clone, because cloning is basically what we're doing. We're taking the original node and creating a clone of that node, and we're cloning all of its neighbors recursively. That's what this recursive.
For neighbors and co-neighbors if neighbor not in clones.
call is, right? And then to the neighbors that we're creating, we're adding them or appending them to the list of neighbors of this node. And so it's actually the last thing to do is easier than you would think. We're going to call depth first search, passing in the original node that we're given in the original function call. And then we're just going to return the result of that, because that's going to give us the connected graph. It doesn't really matter which node we return, I think. So any node that we end up returning is good after the entire clone.
Create a DFS function. We pass in our node. Return old to new node. Okay. Create a copy. Create a copy of that node. We add it to our list, right? And for neighbor in node.neighbors, right? For the neighbor in node.neighbors, where I think I'm gonna need to take a nap. Need to think better.
Clone has been 50 or 60%.
Oh, so to explain this. Adding the clone neighbor to the list of neighbors of the current node's clone. Okay. I understand. Okay. Okay. Makes sense. Requestfully visit neighbors node 2 and node 4. And when we visit the neighbors, we visit neighbors node 1 and node 3. Reclone return copy 1 of boarding. So obviously this is the DFS implementation, right? Let's do the BFS implementation. DQ node, right? While Q, let's do cur is equal to, yeah, Q dot pop left. I want to make for in node dot neighbors if neighbor not in old to new, then we can be cur dot neighbors. Neighbor in cur dot neighbors if neighbor not in old to new. We pop the cur, right? The current node that we're looking at. Then we check its neighbors for neighbor and code.neighbors. We check if the neighbor is not in alt new. If it's not in alt new, I feel like we need to add it, right? So alt new neighbor is equal to, is it neighbor.copy? Oh, is it okay? Node neighbor.val. Okay. Then we have to connect the clone neighbor to the current node. Old to new clone dot neighbors dot append clones neighbor. Turn old to new, old to new node. Whoops. Old to new. Okay. Like this here, BFS. Okay, I'm gonna take a nap really quick, and I'm going to come back. So I'll be back in a second. What's up, guys? I'm back. Took a nap, as you can see. It's dark outside. So for a little longer than I thought, probably about an hour and a half, but we're back. We're locked. We're ready to tackle some more problems. Let's take a look at. I think we've done walls and gates. Let's take a look at walls and gates. I'm just trying to. Walls and gates. Leetcode Premium. Let's try core schedule. Diva is a theater. I'm a hustler. Okay. Looks like a good one. For a total number of num courses you should take, labeled from 0 to num courses -1, you're given an array of prerequisites. For prerequisites I, AI, English, you must take course BI first if you take course AI. For example, if a pair... For example, the pair 0, 1 indicates that to take course 0, you have to take course 1. Okay. Okay, I understand. Num courses 2, periods 1, 0, false. There are a total of 2 courses to take. To take course 1, you should have finished course 0. To take course 0, you should have finished course 1. So it is impossible to reach course 2. Num courses 2, periods 1, 0, true. There are a total of 2 courses to take. To take course 1, you should have finished course 0. So it is possible. Oh, jeez, man. Ugh.
Get that phone out.
Okay. Total number of 2 courses to take. To take course 1, you should have finished course 0. To take... I think these are terrible test cases. Like, no? Yeah, that's what I thought. I feel like they should give way better test cases. These are terrible. Like, turn on. Okay. Jeez, I have a lot of open tabs, dude. What the? Didn't realize I had this many open tabs. Oh, jeez. Okay, so I think the first thing we got to do here is we got to convert this to an adjacency list. To convert it to an adjacency list, we need to create an adjacency list, right? We need to loop through for edge and prerequisites. Edge is equal to AB. And you could AMD. If AJA be not in ADJ. Could have build adjacency list. Okay, then we want to pass in prerequisites. Oh my gosh, dude. Ugh. Here's this graph. I could build graph. Build a graph. For a we initialize it to the empty list. If B not in graph, we initialize it to the empty list. Okay, then we append A dot append B graph B dot append A. We return our graph, right? Have to be in front of it. Okay, so that'll build our adjacency list. Okay, so now there are a total of 2 courses to take. So pretty much I feel like we're detecting a cycle here, in a way, I think. Who has 7 course schedule? Pretty much trying to detect a cycle. Yes, you nailed it. Oh my god, there we go. It means you can't finish all the courses. Okay, so now we have to detect a cycle, right? So how can we detect the cycle? FTFS, pass in our we're gonna need a visited array, right? So visited is equal to set. Okay. We're gonna need okay. We're gonna need a I think we can use DFS or BFS for this technically. Maybe. Okay. For node in graph. Actually, bro, this is so confusing. This shit here. Like, we need a Q. Q is equal to DQ. We pass in node, right? Here. While Q, we want to check, well, our node is equal to Q dot pop left. Okay, so we have our node now. Now we want to look at its neighbors, right? So okay. For I in graph node for neighbor. Yeah, in graph node we want to check, well, if neighbor not in visited, we want to add this node, right? So if neighbor not in visited, we want to add, well, visitor.add neighbor. Okay. Then we want to append our Q, right? Q.append neighbor. I'm going to have a little thing in here. If we find a We just somehow detect the cycle. How do we detect the cycle though? While queue. We want to check, well, kind of just want to return true, right? But somehow we want to have like a return false here, but I don't know how to implement that. I thought this was an undirected graph that I'm looking at now.
Hey everyone, welcome back. Let's write some more neat code today. So today let's look at a graph problem actually. It's called course schedule. We're given a total number of courses and these are our nodes and they're labeled from 0 to n-1 basically. So some courses have prerequisites. For example, if you want to take 0, you have to first take course 1 or as an edge in our graph. So if you want to take course 0, you have to first take course 1. And the only question we want to answer is it possible for us to finish every course? So let's just look at the first example. We're given number of courses are 2, so that means we have one course 0 and another course 1. We know that the prerequisites are like this, meaning that if we want to take course 1, we have to first take course 0, and I'm going to represent it as an edge going outward from 1 into 0. So what do they mean by possible? Let's just run through each of our courses and see, is it possible to take each one? So for 0, is it possible to take 0? Well, we don't have any outward edges from 0, so that means 0 does not have any prerequisites. So it is possible for us to complete course 0. Then we look at course 1. It has one prerequisite, which is 0. And we know 0 is possible to complete, so once we finish course 0, then we're allowed to take course 1, which has no other prerequisites, right? The only prerequisite was course 0. So therefore, both of these courses are possible to complete, so we can return true. So let's look at an example where it's actually impossible. So we're given n equals 2, that means we have 2 courses, 0 and 1, and we're given 2 prerequisites, so 1, 0 and 0, 1. This one means that if we want to finish course 1, we have to first complete course 0, so 0 is a prerequisite. The second one means that if we want to finish course 0, we have to finish course 1 first, so 1 is a prerequisite of 0. So the problem with this is kind of obvious, right? There's a cycle. So if we want to finish course 0, we got to go finish course 1. If we want to finish course 1, we got to finish course 0, and it just goes like that forever. So neither of the courses are possible to finish. So in this case, we return false. So we can actually solve this problem using depth first search. We can also use breadth first search, and I'm going to show you just the depth first search version because I like it better. So given this new example, the first thing you want to do is visualize it. So I'm going to draw a picture. So we're given 5 nodes. So we have 0, 1, 2, 3, 4. That's 5 nodes. We're also given 5 prerequisites. So in this case, we end up having 5 edges, right? From 0 to 1, 0 to 2, 1 to 3, 1 to 4, and 3 to 4. So my goal here is for each of these nodes, I just want to know, right, for each of these classes, can we complete this course or not? And how do we know if a course can be completed? Well, just looking at this picture, it's obvious, right? 0 has a prerequisite of 2, but 2 does not have any prerequisites, which is great. It also has a prerequisite of 1, and 1 has 2 prerequisites, 3 and 4. 3 has 1 prerequisite of 4, and 4, luckily for us, does not have any prerequisites. So looking at this, it's kind of obvious that we can complete all these courses. So let's do the algorithm to be able to determine that. We see that these are kind of our base cases, right? 2 and 4 don't have any prerequisites. That's useful information, but we don't need a graph to tell us that. We can use a data structure called an adjacency list, and I'm going to call it prerequisite map because the data structure I'm going to use is a hash map to represent this. So for each of our courses, we are going to have a list of all of its prerequisites. So for 0, we know 0 has 2 prerequisites, 1 and 2. And we're going to repeat that for every single course. So for 1, we know that 2 does not have any prerequisites, so we can just put an empty list over here. 4 also does not have any prerequisites, so we get another empty list. So now we're going to run depth first search on every single node. I'm going to do it in the order from 0 to n minus 1. So be starting at 0, so we're going to run depth first search on it, right? How are we going to do the depth first search? Well, we have
That's why we need to get the degree.
So we're going to do it recursively. We see that it has 2 prerequisites, 1 and 2. So now let's run depth first search on the first neighbor 1. So now we look at 1. We see that it has 2 neighbors, 3 and 4. So let's recursively run depth first search on its first neighbor 3. So since 3 is a prerequisite of 1, now we want to know if we can complete course 3. So we look at its prerequisites. It only has 1, 4. So now we're going to check its only prerequisite 4. Can we complete course 4? And then we want to look at the prerequisites of course 4, which we know are empty. This is good, right? So now we see that this is empty. So what does that tell us? That tells us course 4 can be completed, which we basically already knew because course 4 has an empty empty prerequisite list. So I'm just going to put a little check mark here to say that we know course 4 can be completed. And so recursively, we're going to end up going back to our 3, and we see that it only had one prerequisite, and we were able to complete that prerequisite 4. So therefore, 3 is also...
Okay, where the hell is my thing? Okay. So, let's get rid of this for now. We don't want to do this here. We just want to print well. Course 1, you need course 0. Do we just get rid of this?
A course that can be completed. And so what we can actually do is, from its prerequisite list, we see 4, we can just remove the 4. We know it can be completed, and so I'm representing that by having an empty list here, right? Just an empty list means that it has no prerequisites, therefore it can be completed, so I removed the only prerequisite that 3 had. Then
For edge and prerequisites, AB edge. If A not in graph, right, we're looking at A right now. So print AB. Why is it not putting the other one in there? Why the hell is it not putting this in here? Bro, I don't get this, bro. I don't understand. I generally don't understand. Like,
From 3, we can actually go backwards to 1, which we see here. We can kind of get rid of this 3 because we know 3 can be completed. And then from the 3, we're going to end up going to 4 to check again if 4 can be completed because it is a prerequisite of 1. And since we already know 4 can be completed, we can get rid of that as well. So now we know for sure that 1 can also be completed. And now I'm going to go back to 0, which is how we even got to 1 in the first place. And we look at the prerequisites of 0. We see 1 is no longer a prerequisite because we basically know that 1 can be completed. But we still have to look at this 2. So then we're going to go to the last unvisited node in our entire graph, which is 2. So now we've gotten to the last course 2. We see it's an empty list, right? Therefore, 2 can be completed. It has no neighbors. It has no prerequisites. So I can put a little check mark here. 2 can be completed. And then we can finally go back to our original node, 0, cross out its last prerequisite, which was 2. And now when we look at 0, even 0 has an empty list of prerequisites. Therefore, we know 0 can be completed. So since we were able to complete every single course, that means we can return true. Every course is completable, and the time complexity for this is gonna be big O, the number of nodes we have, which is n. I'll use n as that, and I'll use p for the number of prerequisites that we had, because if you notice in this graph, we have to visit every single node, and we have to move along every single edge. And once we get rid of the prerequisites from here, we don't really have to visit a course twice, because once we know it can be completed, we can instantly do that. We don't have to go through its prerequisites twice. So I'm going to show you one last example. This is the example that what we're going to do. How are we actually going to detect this loop? Because we see, so I'm just going to cross this stuff out because we're looking at a different example. But here we see that 0 has a prerequisite of 1, 1 has a prereq of 2, 2 has a prereq of 3. So this is a loop. We cannot complete these courses, but how can we actually detect this loop? I'm going to show you how really quickly. So to detect a loop, I'm going to use one last data structure, and it's going to be a set. though I think you could just use an array if you want. I'm going to call it the visit set. And all it's going to contain is the list of courses that we're currently visiting along our depth first search. So let's say we start at 0, then we add 0 to our visit set. We take a look at the prerequisites of 0. We see it has 1 prerequisite. So then we move to 1. So now we visit 1. So we're going to add 1 to our visit set. And we look at the prerequisites of 1. It has 1 prerequisite 2. So then we move to 2. We run depth first search on 2. So to do that, we have to first visit 2. So 2 is also going to be added to our visit set. And lastly, we see 2 has 1 prerequisite of 0. So then we, of course, want to visit 0. And so now we're going to visit 0 twice, but you see that 0 is already in the visit set. Therefore, we detected a loop. Therefore, we have to return false. These courses cannot be completed. So now let's finally look at the code. So the first thing I want to do is create our pre-map. So our list of prerequisites. So we know for each course, initially we can set it to an empty list, so an empty list of prerequisites, and we want to do that for every course that we got, which the number of that is just number of courses. So this is, if you're not familiar, this is some Python stuff. I'm just saying that for every course initially we want to map it to an empty list, and we know that the prerequisites are actually contained in this nested list variable. So let's iterate through that. Let's get each course prerequisite pair from that list and then just start appending them. So pre-map of course, we want to append to this list this prerequisite. So we also want a visit set, which is going to store all the courses along the current depth first search path. And of course, it's initially just going to be empty. So since we're going to do this recursively, I'm going to define a nested function, depth first search, inside of our canFinish function, because then we'll have access to all these variables without having to pass them in as a parameter. The only parameter that we have to pass in is the current course that we're visiting. And so, like most recursive functions, we want to look at our base cases first. The first base case is if course is in the visits.
Bro, what is wrong with my microphone, dude? Like, okay. I want to bang my head against the wall, bro. Take a photo of this. Okay. Okay, graph is equal to for I in num courses. Range num courses. Okay. For A, B in prerequisites, right? Prereqs. Okay. We want to add graph A dot append. I swear to God, this is gonna get the same as the other one. Graph A dot append B, right? Yeah. Let's just do the same as this one. Course Pre. CRS. Pre. Dude, this is exactly what I did before. Like, oh, we didn't return anything. We have to return our graph. It's the same, bro. Okay. Save TFS. We want to pass in what I assume our current node, right? So what will be our current node? Would it be graph 0? Code node, right? We need to call our DFS function. I'm so stupid. We pass in our graph 0, right? We also need a visited set. Visited is equal to set, right? When we think about that solution, what is our base case? Well, base case. For neighbor in range in graph current node to get our neighbors, right? We do well if neighbor not in visited we want to add, right? We'd want to add to our visited set. So visited.add add neighbor. Then we call our DFS function on the neighbor, right? Our base case here would be, well, if come on, man, fucking think, bro. Um, Visited. We know that it's a loop. So we just probably want to return false, right?
Set twice. Course can the pre tells us is that this course has no prerequisites, and we can return.
That's what I was looking for. Okay, if graph cur node is equal to the empty list, you can just return true, right?
True satisfied set because prereq of this on it. Also, we find them. So I forgot to put a not over here. So not x2 from our visit set.
Check out visited. How are we getting the neighbors then? For in pre-map. If not DFS. For neighbor and graph.
If neither of these conditions is satisfied, then we can take this course and add it to our visit set, because that means we are currently visiting this and we're going to recursively run depth first search on its prerequisite. So I'm going to loop through the prerequisites of this course. For each one, I'm going to run depth first search on it. So depth first search on this prerequisite. If it happens to return false though, then we know we can return false immediately. We don't have to wait, because if we find one course that can't be completed, then we can return false for the entire function. So I forgot to put a not over here. So if not, meaning if it returns false, then we return false. But if this does not execute, that means it's a course that can be taken and we want to return true in that case. But before we return true, we want to remove it from our visit set, because we are no longer visiting this. We've already finished visiting it. So visit, remove this course. And also, since we know this course can be visited, what we can do is say pre-map. We can set it to an empty list, so that if we ever have to run depth first search on it again, we will, in that case, execute this condition and return true immediately. We will not have to repeat all this work of running depth first search on its neighbors. So that's all for our depth first search function. The function is done. All we have to do is call it now, but we have to potentially call it for every single course in the number of courses that we have. And if any of them happen to return false, then we have to return false immediately. And if they don't return false, then we can return true. All courses can be completed. And the reason we are looping like this is mainly because what if our graph is not fully connected? Like, what if we have a maybe graphs that are not connected, right? So we have to
shit's so stupid, like. don't think it's gonna make a difference, but I feel like I'm just getting like absolutely cooked on this problem. Like, dude, like, I understand the fundamentals of it, but it's like, bro, you know, why are we removing this at the end? I don't get that. Why are we making our visited? Like, why are we doing that, bro?
So then we know we can return false. Then we can return false for the entire function. So I forgot to put a not over here. So if not meaning if it returns false, then we return false. But if this does not execute, that means it's a course that can be taken and we want to return true in that case. But before we return true, we want to remove it from our visit set because we are no longer visiting this. We've already finished visiting it. So visit, remove this course. We're going to end up going back to our 3, and we see that it only had one prerequisite, and we were able to complete that prerequisite 4. So therefore, 3 is also a course that can be completed. And so what we can actually do is, from its prerequisite list, we see 4. We can just remove the 4. We know it can be completed, and so I'm representing that by having an empty list here, right? Just an empty list means that it has no prerequisites, therefore it can be completed, so I removed the only prerequisite that 3 had. Then from 3 we can actually go backwards to 1, which we see here. We can kind of get rid of this 3 because we know 3 can be completed, and then from the 3 we're gonna end up going to 4 to check again if 4 can be completed because it is a prerequisite of 1. And since we already know 4 can be completed, we can get rid of that as well. So now we know for sure that 1 can also be completed. And now I'm gonna go back to 0, which is how we even got to 1 in the first place, and we look at the prerequisite.
Man, I feel like that was just such a tough problem, bro. Like, so frustrating, bro. Is this a new problem for the day, bro? Yeah, this is a tough problem. Man, bro. Go with a little finish of a little binary surge, bro. Low key. March 14th. We're playing the guess game. The game is as follows. I pick a number from 1 to n. You have to guess which number I picked. You call a predefined API and guess it now, which returns 3 possible results. -1. Okay. Low is equal to 0. High is equal to n. While low is less than or equal to high. We want to calculate our midpoint, right? Mid is equal to plus low over 2. Okay. I want to check, well, allow API if guess mid is greater than your guess is higher than your guess is lower. Is equal to -1. Then we want to, your guess is higher than the number I picked, right? So then we want to set our high to be equal to mid. Your guess is higher than the number I picked. This is equal to mid -1. If guess mid is equal to -1, equal to 1, your guess is lower than the one I picked, right? So we'd make our low equal to mid +1. If our guess mid is equal to 0, then we would return mid, right? I want to return yes, it doesn't exist, right? Nice, bro. Let's go binary search, bro. Let's go. Cocoa eating bananas, man. The problem is so AIDS, bro. Turn the index. I need the peaks. You're given a 0 index integer array nums. Find a peak element and return its index. If the array contains multiple peaks, return the index to any of the peaks. Okay, you may imagine that nums -1 is equal to none. In other words, an element is always considered to be strictly greater than a neighbor that is outside the array. You must write an algorithm that runs in O of log n time, which obviously means binary search. Um,
Well, doesn't the array need to be sorted in binary search? Does the array need to be sorted for binary search? Yeah, that's what I thought. Okay, so let's sort our array. Nums.sort. Let's print nums. Cool. If we sort the array, doesn't it mean it won't be fast enough? No? Question doesn't say the array's sorted. How we know to use binary search? Has sorted subarrays. on for, bro? Oh, jeez. I'm probably going to cut the video. It's been a little while. I didn't realize how... Oh my gosh, dude. What is going on here? Oh no, dude. Oh no. What is going on with my computer, dude? Oh no, now I can't cut the video.